In this video, we're going to discuss ethers and epoxides. We're first going to talk about the nomenclature of ethers and epoxides. In the IUPAC nomenclature, ethers are not treated as a special functional group. What that means is that they don't get a special ending and they have no priority for numbering. Instead, ethers are just treated as a special type of substituent on a separate parent chain. The substituents are named according to the methyl group of the smaller carbon chain that would be not the parent, and then adding the ending oxy. Here's a couple of examples. If we look at this molecule has a 6-carbon cyclohexane ring, then an oxygen, and then a 1-carbon methyl group. We would select the 6-carbon cyclohexane ring as the parent because there is no special functional group and it's the longest carbon chain. So the parent becomes cyclohexane. The substituent then is a meth because it's a 1-carbon group with an oxygen, oxy. We call it methoxy. So the correct IUPAC name for this would be methoxy cyclohexane. Here's another example. We now have 2 straight-chain carbon groups. The one on the left has 3 carbons. The one on the right has only 2. So we select the carbon chain on the left to be our parent. Because it has 3 carbons, it is a propane. We then choose this group to be an eth, because there's 2 carbons, oxy, substituent. And because we have a straight chain propane, we have to indicate that the ethoxy is attached on carbon 1. So the name is 1-ethoxypropane. Ethers have a semi-systematic common naming system that is used very often for ethers that have small carbon group substituents. In the common naming system, what we do is we name each alkyl group and then we add the word ether following the 2 alkyl group names. If we look, for example, at this one, our alkyl groups are a methyl and an ethyl. So we would call this ethyl, then a space, methyl, then a space, ether. Note that the alkyl group names have been put in alphabetical order. This is the modern way to do it. It used to be that the groups were arranged in order of increasing complexity. So sometimes that would give the opposite order to what we do in modern. If the 2 groups are the same, for example in this case where we have 2 ethyl groups, we do not call this ethyl, ethyl, ether. What we do is we abbreviate the 2 groups using the di prefix. So ethyl, ethyl becomes diethyl ether. This is the most correct common name. However, in the original common nomenclature, it was very often the case that if the 2 groups had the same name, then the name would be written once, and since it was an ether, it was known that you had to have 2 carbon groups, so it was assumed that they were both the 1 carbon group written. Therefore, very often you will see this substance named as ethyl ether. Finally, just to make it even more confusing, because ethyl ether itself is such a commonly used chemical, organic chemists took to calling it just ether. So if somebody asks you to get a can of ether, what they're really asking for is a can of diethyl ether. Finally then, if we look at this one, we have this group on the left and that group on the right. So the group on the right is a methyl, and I just wanted to include this to sort of review that this group here, which is a 2-carbon group with a double bond, is called vinyl in the common nomenclature. So this is called methyl vinyl ether. We can also have cyclic ethers, which are rings that have an oxygen substituted in for one of the carbons. These have, several of these have common names that are widely used, and in fact, some of them form the basis for names of other molecules, such as important biomolecules like carbohydrates. This ether is the first one I want to discuss. Its name is furan. If we take furan, which has 2 double bonds in the ring, and we treat it with hydrogen and palladium, the double bonds would absorb the hydrogen, they would become single bonds, and we would add 1, 2, 3, 4 hydrogens. That would create this molecule, which is the 5-membered cyclic ether with no hydrogens. Because we made this molecule by adding 4 hydrogens to furan, this molecule was given the name tetrahydrofuran, 4-hydrogen furan. This is a very commonly used solvent. In fact, it's so commonly used that organic chemists have given it abbreviation. The abbreviation is THF. The 4-membered cyclic ether is called oxetane. This is a 6-membered cyclic ether which has 2 double bonds, very similar to furan, and it is called pyran. Again, if we completely hydrogenate it, pyran would absorb 4 hydrogens, becoming tetrahydropyran. And finally, the common name for a 3-membered ring cyclic ether is oxirane. We'll be using that to name epoxides in a section below. Epoxides are a special type of ether which exists as a 3-membered ring. We've already talked about how we can make them, and we're going to talk about some of their reactions later this chapter. The problem with naming epoxides is that there are several different systems in use. The first system is probably the oldest system. It's what I call the alkene oxide system. It's derived like this. Epoxides are often prepared from alkenes. So for example, if I take just this generic alkene and then I treat it with a peroxycarboxylic acid, the double bond will become a single bond and we will add an oxygen ring to the 2 former carbons of the double bond. Knowing this, chemists first started naming epoxides as the oxide of the Knowing this, organic chemists first started naming epoxides by considering them the oxides of a known alkene. So for example, if we were to have cyclohexene, which would be this molecule, and we were to make the epoxide, we would get this molecule. This would be the oxide of cyclohexene. In other words, cyclohexene oxide. Similarly, the common name for this molecule is ethylene. If we were to make the epoxide out of this, we would get this. This would be ethylene oxide. The confusing thing about this naming system is that the name contains the ENE ending in one of its parts, but the actual molecule has no double bond. So this is not really my preferred naming system, but it is widely used, and so you probably need to become familiar with it. The second naming system treats the epoxide as a substituent that is attached to two adjacent carbons. The substituent name is epoxy. So here's an example. This is particularly useful when the molecule has other important functional groups. This particular example is actually an alcohol. So what we're going to first do is name the parent alcohol. The parent alcohol has 4 carbons in it. The hydroxyl is attached at carbon 1, so this is butane 1-ol. But then we have, connecting carbons 2 and carbons 3, this epoxide ring. So we would add in front of that as a substituent 2,3-epoxy, making the entire name 2,3-epoxy butane 1-ol. It's my belief that this is, in most cases, the simplest way to name an epoxide, particularly of a complex molecule. There is one more way that is used to name epoxides, and that is to name the epoxide as if it is a 3-membered heterocyclic ring. Remember, the 3-membered heterocyclic ring is called oxirane, with substituents attached to it. When we name it this way, the oxygen is number 1 atom of the ring, so the substituents could be attached on carbon 2 or on carbons 2 and 3. If we look at this example, our oxirane ring has a methyl group on carbon 2 and a methyl group on carbon 3, so it would be 2,3-dimethyl oxirane. We also have wedges and dashes in our picture, indicating stereochemistry. In this case, one methyl group is on a dash, the other group is on a wedge, so this would be trans 2,3-dimethyl oxirane. Just as a side note, we could also use RS naming because these are chirality centers, but in this case, trans will be sufficient.